In this section, we are going to talk about evaluating limits analytically. So this means evaluating limits by a method other than graphing or just plugging in points as x approaches c from either side. So the first thing we want to talk about with regards to this is some properties of limits. And we know from the examples that we've seen that the limit of f of x as x approaches c does not necessarily depend on the value of f at x equals c. Now, it may happen that the limit of x as x approaches c of f of x is equal to f of c. And in this case, we say that this limit can, or a limit that satisfies this can be evaluated by direct substitution. So there are certain categories of functions which can have a limit evaluated by direct substitution. So these are some really basic limits. If we let b and c be real numbers and we let n be a positive integer, number one, the limit as x approaches c of b is equal to b. Number two, the limit as x approaches c of x is equal to c. And number three, the limit as x approaches c of x to the n is equal to c to the n. So these are all limits that can be evaluated by direct substitution. Whatever x is approaching, you plug it in for into the value, the variable x in the expression. So notice there's no x here, that's just a constant. Here you just have x equals c, and here x to the n is c to the n. You just plug it in. So we're going to prove theorem 1.1 number 2. And we're going to do this proof using the epsilon delta definition of a limit. So I'm going to start by letting epsilon be greater than 0. And in this case, we're proving that the limit as x approaches c of x is equal to c. So c is just going to be c. That's what we're looking at there. F of x is x, and L is equal to c also from this part right here. So we're going to assume that the absolute value of x minus c is between 0 and delta, and we want to get down to the fact that the absolute value of f of x minus L, which also happens to be x minus c, is less than epsilon. So then therefore, by the definition, the limit as x approaches c of x is equal to c. Well, normally what we would do at this point is we would try to find the delta that makes all of this work, but we're trying to get from x minus c absolute value is less than delta to the absolute value of x minus c is less than epsilon. So if we just let delta equal epsilon in this case, that's the one that we're choosing, we're already there. So this proof is done. Next, we're going to use these properties to evaluate some very simple limits. The limit as x approaches 3 of 45. This would be our b, okay? And we know that the limit as x approaches c of b is equal to b. So in this case, the answer is 45. For the next one, we've got the limit as x approaches 14 of x, and if you just plug in 14 for the x, you get 14. And for this next example, this is one of those x to the n. So the limit as x approaches negative 4 of x squared is going to be negative 4 squared, which is positive 16. And that is the answer. Now you can verify this by graphing these functions, f of x equals x, f of x equals x squared, so on and so forth. And you will see that that is the point that they approach. Some additional properties of limits are shown here if we let b and c be real numbers and n be a positive integer, and we let f and g be functions with the limits. The limit as x approaches c of f of x equals L, and the limit as x approaches c of g of x equals k. If you have a scalar multiple of a function, you can just multiply that scalar b by the limit of the function. And also the sum or difference. If you have the limit of the sum or difference of the two functions, that's just the sum or difference of the limits. If you are multiplying two functions, you can multiply their limits. Now this is assuming we're approaching the same c in all of these places. If you are dividing two functions, you can divide the limits provided the denominator limit is not 0. And if you're raising a function to an nth power, you can raise the limit to the nth power as well. So just an example that you might see for one of these types of problems. We don't know anything about what f of x and g of x are in terms of their equations, but we do know that the limit as x approaches 4 of f of x is 12, and the limit as x approaches 4 of g of x is negative 6. So if we wanted to evaluate the limit as x approaches 4 of f of x plus g of x, we can do that by adding their limits. So this is just the limit as x approaches 4 of f of x plus the limit as x approaches 4 of g of x, which is going to be 12 plus negative 6, which is 6. In this case here, we've got the limit as x approaches 4 of f of x divided by g of x, so that's the limit as x approaches 4 of f of x divided by the limit as x approaches 4 of g of x, provided that this limit down here is not 0, which it isn't. You can see it up here. So this is 12 divided by negative 6, or negative 2. Similarly, we'll recall with these two problems that the limit as x approaches 4 of f of x was 12, and the limit as x approaches 4 of g of x was negative 6. So in this case, this is going to be 3 times the limit as x approaches 4 of f of x, which is 3 times 12, which is 36. And with this last one, you can make this the limit cubed. So the limit as x approaches 4 of g of x was negative 6. So this is negative 6 cubed, which is negative 216. Now just to kind of recap what we've talked about so far, we know that we can take the limit of constants of x and of a power of x, and we know that we can also take the limit of constant multiples of any function that we know how to take the limit of, and as well as the sum or difference in the multiples and all of that. So putting all of that together, we have the building blocks to evaluate the limits of a polynomial, because a polynomial, remember, is just a it's a sum or difference of powers of x multiplied by constants, or just a constant at the end. So this is what theorem 1.3 says. It says if p is a polynomial function and c is a real number, then the limit as x approaches c of p of x equals p of c. So you can just plug c directly into that polynomial. And because a rational function is just the quotient of two polynomial functions, if r is a rational function given by r of x equals p of x over q of x, and c is a real number such that q of c is not equal to 0, we can also evaluate the limit as x approaches c of r of x by just plugging in c into that function. So since we can evaluate limits of variables raised to a power, scalar multiples of variables, and the sum or difference of those terms, we can evaluate the limit of a polynomial function or a rational function using direct substitution, assuming that that denominator is not 0. So let's take a look at some examples. I've got the limit as x approaches 3 of x cubed minus x squared plus 6. So I'm just going to direct substitute. So this will be 3 cubed minus 3 squared plus 6. So 3 cubed is 27, 3 squared is 9, and we've got the plus 6 on the end. And all of this simplifies to be 24. With this next one, you just want to watch your negatives. So we're going to have negative 1 squared minus 7 times negative 1 plus 2, which is going to be 1 plus 7 plus 2, which is 10. And then for a rational example, I've got this one right here, and we just want to check if I plug a 0 into this denominator, I get negative 6, so we're okay there. We can just direct substitute that. So that'll be 5 times 0 to the 4th minus 3 times 0 squared plus 24, and that's all divided by 0 minus 6. So that is 24 over negative 6, or negative 4.